Good day, Math 30-2s. Today we're in Chapter 4 talking about rational expressions. Now, Chapter 4 is basically all about fractions where you might be involving some variables. Now, the point of the first lesson is to talk about equivalent rational expressions. Now, a rational expression is essentially, if you think about it as a fraction, there might be letters in it. And an expression is kind of the other side of an equation where you don't have an equal sign. It's just a statement like 1 divided by 2 is a rational number. It's also an expression. I'm not saying equals x or equals something. It's just an expression without an equal sign. Equivalent has the word sort of equal in it. So if I were to say 2 divided by 4, this is also the same as 1/2. So today we're talking a little bit about how 2 over 4 is an equivalent rational expression to 1 over 2. But the expressions are going to be a little bit more complicated and a little bit more complex as we start to talk about variables and polynomials. So our point is to determine if two rational expressions are equivalent. Rational, think about rational as a fraction. Determine if two fraction or rational expressions are equivalent, and determine any non-permissible values. And we'll get to that non-permissible part a little bit later. As a quick investigate, imagine you are on Amazon purchasing some items online, and you're thinking about getting a new Lightning or Type-C cable for $8, but shipping costs $4 because you didn't get Prime. Question is, determine the cost per item depending on how many cables you purchase. I'm going to organize this kind of simply with the number of items that you purchase and how much it is going to cost you per item. So if you were to purchase one item, how much does it cost? Well, it's $8, and the $4 shipping means you're going to pay $12 to get that one item to your house. If you were to purchase two items, it's now going to cost you $8, and another $8 is $16, plus the 4 is $20 per 2 items. It ends up costing you $10 per item because they're kind of sharing that shipping charge. If we were to buy 3 items, we're spending 8 groups of 3, 8 groups of 3, 3 groups of 8, so $24, and the $4 is $28 for 3 items. Turns out to be $9.33 per item. Because again, now you're sharing $4 between 3 items. Now, what's happening here is we're looking at the cost per item getting cheaper and cheaper because everyone's sharing the shipping cost. So we're basically looking at if we throw in a letter here to make this a little bit more broad, we could say it's $8 for every item if X represents the number of items. So $8 times the number of items, plus you've got this $4 for shipping that's fixed. And we're going to divide this by the number of items that you purchase. This is actually a rational expression. It's a fraction. It is involving letters. But this is what we're going to start to see more in Chapter 4. Now, determine a cost per item equation. This is a really interesting way of looking at a cost per item. What if you were to buy 20 items? You put a 20 into the X, and it's going to tell you exactly how that sharing of the shipping costs is going to impact. And so in a business, often the more items you buy in bulk, the cheaper your margins are going to cost. So there are a lot of equations that can exist. In junior high, we talked a lot about linear functions, and this was focused on in grade 10. Quadratics was focused on in grade 11. Exponential, logarithmic, cubic, sinusoidal are things you may not have heard of just yet, but we'll get to experience those in this course. But there's a lot of different equations that model how the world works. Linear can be used to represent things like costs. So just this top part, $8 per item times the number of items, add $4, that's your total cost. So just that top part is an easy way of totaling up your costs. Quadratics often involve things like gravity. Exponential functions are often in things like finance and maybe population growth of bacteria. But when you start to deal with fractions, immediately our brain is going to start to go towards rational expressions. So think about fractions and rationals as being kind of very, very related. Now, our definition of a rational expression that we're going to try to really, really simplify is that a rational expression is a fraction with a polynomial on the top and the bottom. Now, a polynomial is also something we might have to define. A polynomial you can think of as either being, think about linear or quadratic or eventually cubic functions. So a polynomial is something that doesn't have any square roots, doesn't have any weird negative powers. Think about these examples as we try to articulate what a polynomial is and then what a rational expression is. Here is a linear function on the top and a quadratic on the bottom. Another example of a rational expression might be linear on the top and maybe a constant like 5 on the bottom. You could consider this a rational expression. But we can look at maybe what it isn't. It's not going to be square root of x on the top. That's not linear and that's not quadratic. That's not cubic, even if there is something linear on the bottom. Another example of what it isn't, 2 to the power of x. That's not actually quadratic. This is 2 to the power of x. This is exponential. And on the bottom, I could throw in something a little deceptive like a quadratic. But what you're looking for in a polynomial is your powers to only be whole numbers like a 0, 1, 2, 3, 4, and so on. That's largely what you're looking for. Now, in science, we often learn that velocity is distance over time. What is the velocity if you travel 30 kilometers in 0 seconds? How fast were you traveling if you traveled 30 kilometers in 0 seconds? Well, if you think about it logically, that doesn't really make a lot of sense. How can you travel 30 kilometers in no time? There really is no answer to this kind of logic. So there is a generalization we can make about zeros, and that is that you cannot divide by 0. Now, even though we looked at this in a very specific context, this is a statement we can make about rational expressions that you can never divide by 0. So we start to define something called a non-permissible value. A non-permissible is a non-permitted or not allowed value. So a non-permissible value is a value which cannot be used. Now, this will sometimes get shortened to an NPV, or sometimes we call this a restriction. Non-permissible value, restriction, NPV, these all refer to a value that you cannot use. So what if I were to say 5 divided by x? What on the bottom could you not use? Well, if the bottom was a 0, that's a problem. If the bottom is a 0, that's a problem. X cannot be 0, that's a problem. You might look at this next one and say, what if I put a 0 on the bottom? Well, let's be careful when we say what can't be 0. X is allowed to be anything we want. It's the bottom that can't be 0. I'm going to take this bottom and say the bottom expression cannot be 0. It's a little mini equation. Treat this like we're solving for x, and subtract 1 from this side, subtract 1 from this side, and what we end up with is that an x cannot equal -1. -1 is actually our non-permissible value in this case, because if you replace this x with a -1, you get -1 plus 1, they cancel out, you get a 0 on the bottom, and that's the value you cannot use. Things get a little bit more complex when we look at things that are just more complex. And a good rule of thumb is to always factor, if possible. This will be a reoccurring statement throughout chapter 4. Factor if possible. Now that bottom, it's really hard to see what plugging in would make the bottom a 0. So I'm going to actually look at that bottom and say, all right, I want this x squared minus 2x to never be a 0. So when is x squared minus 2x going to be 0? That's a problem. We solved questions like this in grade 11 in the quadratic equations unit, and to do this we either factored it, which means you try to break it apart into two things that are multiplying, involving brackets, and one of the ways is to take a common factor out. I see an x there and an x squared in these two terms, and if I take an x out, we're left with an x, because x times x is x squared, and a minus 2 because x times the -2, x times 2, 2x. I'm left with this. And this next statement is called the zero product property, and if you've got two things that are multiplying together and are trying to equal 0, we can look at them individually. And we can say, when this left side equals 0, it's going to get us to one of our true statements. And if you look at the other product, your other factor, if you make that statement equal 0, both of these will hold true as they did last year. So we've got x equals 0 as a statement, and a little bit of work to say plus 2, and say x is equal to a positive 2. And now if we think about these two values and why it works, if I say x equals 2, at any point along here, if I plug a 2 in, it's going to give us a problem. 2 minus 2 makes this bracket a 0. 0 times 2 is a 0. This whole thing is back to a 0, and that's not good because this is the bottom. 2 squared minus 2 times 2, that's a 4 minus 4. That is true. That makes this a 0 on the bottom. So both of these, 0 squared minus 2 times 0, would be a 0, and both of these would be non-permissible values or restrictions. So part of this unit is a little bit about being cautious and being careful about what values we're saying are okay. Now, in Math 30-2, Alberta Education has said that we are asked to determine equivalent forms of rational expressions. We are going to be limited to numerators, top, and denominators, bottoms, that are monomials and binomials. So monomials is one term, like x, or 3x, there's no addition, or binomials, like x plus 1. There's two terms separated by addition. Or the bottom will be x squared minus 2x. Two terms separated with a subtraction. So we're limiting to monomials and binomials. So your questions will only have monomials or binomials for you to have to factor. So the last example involved some complex thinking. There was some factoring to do. Let's consider some grade 11 factoring and quadratic equation techniques. Factoring out a greatest common factor is one key way of factoring. We have to look at the 15 and the 30 and say, we're going to take out something that's common between them. Now, if you need to go back and say, what are the numbers that could multiply together to make 15? It's a 1 times a 15. It's a 2 times something. Does that make 15? No. A 3 times 5 makes a 15. And there's actually nothing else. The 30, all the factors of 30 are 1 times 30. If you go 30 divided by 2, you do get an answer, 15. 30 divided by 3 gives you a 10. 30 divided by 4, decimal. 30 divided by 5, a 6. And those are the only things that could create 15 and 30. These are all the factors of 15 and 30. What's the greatest common one? Well, they share a 1, they share a 3, maybe it's 3. Oh, they share a 5. I think they share a 15. This is the greatest common factor. So we're going to take a 15 out of both of those by dividing. Now, this can easily get a little bit confusing. So what I'm going to do is I'm going to say we're going to divide a 15 out. What results is an x plus a 2. But we took a 15 out. And it's very, very important to make that 15 show up in front. So when we take it out by dividing it out, we're saying we're leaving it out in front as the product to recreate this. This original statement and this new statement are saying the same thing. 15x plus 30. But it looks a little bit different. So we start to get a little bit more comfortable by saying what's common between a 6c and a 4c squared. Well, again, if you really, really wanted, you can say, what's the list? What's the list? The greatest common factor in this case is a 2 and a c. Now, you can see that if you divide both of these by a 2c, we end up with a 3, because the c's cancel, those cancel. Here we're left with the c squared on top. That's a c and another c, canceling with this c. And we're left with a single c, but also a 2 from the 4 divided by 2. So we took out a 2c, and we're left with 3 plus 2c. Being able to factor confidently is going to make all of our work much more simple. Now, for the next one, we can take out a 2 and an x squared, leaving us with an x minus a 4. If you feel like it helps to write a 2x squared underneath, show how it cancels, see what's left over, great idea to continue to do that, but it depends on your confidence level. So again, you could say divide by your 4m cubed m squared. Good trick is to pick the lowest number of m squareds, the most number of m squareds that are shared. It's like this one has 3 m's to share, this one has only 2 m's to share. They can both share together the same amount, an m squared only. So m squared will be shareable together, n squared shareable together, and we can take out a 4, leaving us with 4 times 2 is 8, m squared times m is an m cubed, and n squared times 1 is an n squared, and what's left over is a 1. This is a very common mistake to forget that 1, because you need to have a binomial here, 2 terms, so if you were to distribute this back in, you need that 1 there to recreate this last term. Otherwise, if you forget it, you're only going to multiply those 2 together, and the first term shows up only. And so this last one, again, your greatest common factor is a 4, x squared y. Feel free to pause these at any time. And you're left with a 3x plus a 4y. Final answer. Now this is factoring a greatest common factor, and this is the first type of factoring you should always try to do if you're about to factor. Always take stuff out. The last type of factoring that we need to know how to do is factoring a difference of squares. A difference is subtraction. Squares are numbers like 9, 4, 16, 25, because 3 times 3 is 9, 2 times 2 is 4, 4 times 4, 5 times 5, and maybe even things like 9y squared, because 3y times 3y will get you that. A square is when you've got something times itself happening at its root. So here you've got an x and a 2 as sort of the root of each of those. There's a subtraction of 2 squares, and in a difference of squares, there's a nice trick. You can actually take the root of each of those numbers, x and a 2, and write it twice. One gets a plus, one gets a minus, and the reason we do this is because you're going to recreate your x times x, x squared. X times 2 is a 2x. A negative 2 times a x is actually going to cancel out. And the last term is a negative 4. When you do this, we'll say trick, what it does is it'll always have those middle terms cancel out, and in a difference of squares, you can always focus on writing the root, recognizing a subtraction to make this a difference of 2 squares, and then write out that binomial twice. 2x and a 3. 2x and a 3. One gets a plus, one gets a minus, and the order really doesn't matter. See how this was minus plus, and this is plus minus? The order doesn't matter. 3x, 4y, 3x plus 4y, 3x minus 4y. This type of factoring is really, really fast if you recognize it. You can have questions that are a combination of greatest common factor and difference of squares. This is a difference of squares, but you don't see it yet. You can take a 2 out, leaving you with an x squared minus 4. Now this is a difference of squares. And we can say x2, x2, one gets a plus, one gets a minus. So always try to do a greatest common factor before you start any question. 2x comes out, x squared minus 4, 2x, x plus 2, x minus 2. X can come out, x squared minus 16, x minus 4, x plus 4. So there is some complex things that might start to happen, but as we start to get confident with our factoring, we get to apply that quadratic equation solving from last year where we can ask for what values of x would this equation be true. This is again that zero product property, two things multiplying together to equal 0. We can look at each of these parts or factors to produce a little mini equation equaling 0. So 3 equals 0, x squared, x minus 2 equals 0. Only an x is really going to give us an answer, so this doesn't really do anything for us. But x minus 2 equals 0 is an equation I can solve, and I can add a 2 to this side, plus 2, that cancels out, and x equals 2 is a solution to this equation, because if I put a 2 right here, 2 minus 2 is a 0, 0 times 3 is in fact 0. So 2 is the only solution to this. Here, little mini equations, x equals 0, x minus 5 equals 0, x add a 5 over equals 5. 2 solutions this time, because if you put a 0 right here, 0 times, I don't care what that's going to be, negative 5 technically, but 0 times anything will be a 0. Factoring helps to solve these. If I take a 5 out, x minus 3 equals 0. 5 isn't an x, it's not going to do anything for us. I'm going to even just ignore it for the moment and say x minus 3 is 0 and solve that little mini equation, x is 3. Factoring, this is a hard equation to solve if you just stare at it and say, what would x need to be for this to be true? But if you factor it to 2x, you're left with an x minus a 3, and I'm doing that a little bit quick now. And you can say, all right, mini equation. How do you solve for x? What's the opposite of x times a 2? Divide by a 2. X equals 0 divided by 2. X is a 0. X minus 3 plus 3 plus 3. X equals positive 3. Difference of squares. Aha. Again, going a little bit quick. X plus 4x minus 4 equals 0. Little mini equations. When does x plus 4 equal 0? When x equals negative 4. X minus 4 equals 0. X equals positive 4. And the last one here, divide out a greatest common factor of a 3. I noticed immediately that this wasn't a difference of squares because 3 isn't a perfect square, but then I recognized I can divide 27 by 3. So now I can say x squared minus 27 divided by 3 is a 9, and that's perfect. x minus 3, x plus 3, and I get my two little mini answers. The 3 doesn't really help us out, but any letters will. X equals 3, x equals negative 3. So that one has two answers. So we need to kind of keep building this idea of what is a rational expression, what is some ways to factor, how do we solve equations. So when we get questions like, all right, with confidence, tell me the non-permissible values of this. We can focus on that denominator and say, I can let that bottom be 0, that's a problem. And if I solve this bottom for when it's a 0, I can say the solution for the bottom being 0 is x equals 3. And I want to say that's not allowed. It's a non-permissible value. The bottom can't be 0. Hard to guess at the bottom one unless we make a little mini equation and say the bottom cannot be 0. And for the moment, just say, when is the bottom 0? I can do this in two ways. I'm going to actually get creative here and make that 2x a positive. So I can add a 2x, add a 2x, and make it appear on the other side as a positive. And then I can get rid of this 2, which is a multiplying x times 2 by dividing both sides by 2. And this leaves me with x equals a 5 over 2. So that's the value of x that would make the bottom 0, and I don't want that. So I have to say it's not allowed. I'm going to leave these last two as a try later so we can move on to some bigger questions that are about equivalent rational expressions. Here's a statement that says, determine an expression for the following restrictions. If the bottom is not allowed to be a 1, I can say, all right, x is not allowed to be 1. That means, and if I go in the opposite direction of the last page, that means the bottom would be a 1. The bottom would be 0 if x is 1. And if I subtract the 1 over to this side, I could make this say x minus 1 equals 0. So if x is a 1, this is a problem. So if I write that on the bottom, now this has a statement that says if a 1 is put right there, this whole thing doesn't really work. And I really don't care what's on the top. I could say 5, I could say 7, I could say 5x plus 2, whatever it is, the bottom is what's most important. For two restrictions, if I say x cannot be 1, I can take that same factor, x minus 1, and say, well, that's a problem. And if I put an x on the bottom, that means if I put a 0 right here, immediately that 0 is a problem because 0 times anything is going to make the bottom a problem. So any number on top, I really don't care. But you can kind of think backwards to create an expression to work backwards. Equivalent fractions. Get into the heart of today's lesson. Determine 3 fractions equivalent to 1/2. Times 2, maybe. And make this 2 over 4. Maybe times 2 again. Times 2 again. Maybe times 3. Times 3. All of these are equal to 1/2. So why are we allowed to multiply an expression by a number like times 2 times 2 to create an equivalent expression? Shouldn't multiplying it by a number change its value? Well, we double the top and the bottom, and what that does, if you think about maybe something like a square pizza, here is 1/2 and 1/2 of a pizza. If we double this to say there are now 4 pieces, we double the number that we're talking about, and so we're still talking about the same amount of pizza, but now we're talking about 2 pieces out of 4 versus 1 pizza out of 2. We basically doubled the number of pieces that we're talking about, and we double the size, the number of pieces that we are examining as the whole. So we have to multiply the top and bottom. If we only multiply it by the top, we definitely start to change things. So how about 1 and 1? Is that the same as x and x? Well, if I times the top by x and times the bottom by x, are they equivalent? You bet. As long as x doesn't equal 0. And then it's all allowed. But it's a strange thing to say, yes, it's always the same because times x will get you to this. But just be careful. We're not allowed to say 0's what x is. Everything else is all good. Example 2 asks to write an equivalent expression to this by multiplying by x over x. So we can multiply by any number we want, like 2, but here we're going to multiply an x on the top and an x on the bottom. So if we take this fraction, multiply the top by an x, multiply the bottom by an x, we end up with x times x plus 1, x times x minus 4. Done. This is an equivalent rational expression. We could tidy it up a little bit and say x goes into the bracket, and that distribution results in an x squared plus an x. The bottom is an x squared minus a 4x. And this is an equivalent rational expression. And that ends 4.1 as we continue in Math 30-2, Chapter 4, Rational Functions.